We'll give it 2 more minutes and then we'll get started.
Sure.
All right. Good morning, everybody. Thanks for joining us. It's 10 o'clock, so we're going to get started with this workshop on Ex-Ante Lifecycle Assessment of Emerging Technologies. I'm Stefano Cucuracchi from Leiden University, and together with me today, Dr. Flora Siebler, who will in a moment introduce herself and present the content part of the workshop, and Dr. Indranil Sen, the project manager of the PROGENY project and who is based at UASABI Innovations. I'd like to thank UASABI Innovations for organizing this workshop. And we will get going in a moment. I will let Indro first tell you some words about the PROGENY project, about the context of the project partners you also see in the background here represented. And then Flora will get going. I will also monitor the chat. If there is any question, any technical difficulty, just let us know. We will try to solve those. We have some technical support on the line just in case. And also, we will have as you can see on the workshop agenda on the slides, we will have some moments for you to ask questions. We divided the presentations and the content part of the workshop in some blocks, and then there will be some time for Q&A. Indro, I'll leave the word to you for some words on PROGENY. Thanks for joining us.
Good morning from sunny Torino. It's sunny outside, but the window, or rather the door behind me, is closed for contrast. So my name is Indranil Sen, and in short, Indro. I represent UASABI Innovations, who's a dissemination, communication, and exploitational partner at the project PROGENY. Also, I want to mention here that the project is being coordinated by Technical University of Dresden, by Professor, and the coordinator is Professor Carl Leo. I work as the project manager right now, and also mainly the dissemination, communication, and exploitation manager. I thank University of Leiden and Stefano and Flora for coordinating this workshop, and I hope that everyone who is attending enjoys it. And this recording will be available through the website of both UASABI Innovations and the project, which is progeny-project.eu. I want to just say a very few words about the project PROGENY. What is the motivation behind it? And it is the electronic waste that we have created. Very interestingly, the electronic devices that we have today and the sensors and gadgets and everything that pretty much runs the show in the modern world, they are unsustainable. It starts from the birth of the raw material, which is through mining of metals and semiconductors, And throughout the processes that are involved in giving shape and architecture to these building blocks, starting from the materials, each process involves a very large scale destruction of natural habitat and in the environment. So on one hand, we are highly dependent, the society is highly dependent on electronic technologies, electronics and electrical engineering. And on the other hand, we clearly recognize that this is an unsustainable system. The future takes significant steps for an evolution of the machines and the sensors and devices that we use today in order to be sustainable and really for the society to serve. So we took this decision, and this was not evident because the status quo, the incumbent is fully electronics and electrical technology, but we took we look forward towards to nature in order to have our inspirations for our designs, our engineering and scientific designs. And when we look to nature, we see that nature is working on protons and ions. Living systems are working on protons and ions, and they're very efficient, and they're symbiotic. So we try to think of designs of systems, of electromechanical systems based on living matter, based on an archetype that represents living matter. And we found very interestingly that soap films are very interesting starting points because they are nanotechnology of water in action, not just water, but water-based nanocomposites. So we started the concept, the PROGENY project, and we submitted this proposal, and fortunately, and also that it resonated with many people, evaluators, and it was funded. And we are in the first year of the project, and the project is going excitingly well. Everything is in place, so I'm extremely happy as a project manager. And with this, I request that all of you please take a look at the project website. We have a forum, we have comment sections. Please read our blog page where the researchers will be posting their thoughts and ideas. Please make comments. Please participate in the project as peers and supporters and enthusiasts. And with that, I give the floor to Stefano and Flora for today's workshop on life cycle assessment, which I think is a crucial part in development of any new and emerging technologies, because it gives us a feedback to go back to our drawing boards in case we are again creating a Frankenstein's monster out of good wishes. So we must keep a track and be responsible researchers, and Ex-Ante LCA empowers us to do so, to be so. So thanks a lot, and I look forward to the rest of the workshop. Thank you.
Thanks a lot, Indra, and we will hear a bit in the last bit of the workshop a bit more about PROGENY and the challenges of doing life cycle assessment or ex-ante life cycle assessment at the earliest stages of innovation. But Flora, floor is yours to start.
Thanks a lot for the introduction, and I already see that we are not staying in the timeline. I hope you can excuse that. And I also have to say that I will look in the other direction. I have the luxury of having 2 screens, but just 1 camera, which is in my laptop. So I'm sorry for that. So we have 5 parts today. The first will be a general introduction, because not everyone who is participating knows about life cycle assessment. And then we have also the third part that's a little bit going more into life cycle assessment and the first part of the life cycle assessment. the functional unit definition. And then the second one, it is showing what is ex-ante life cycle assessment really about. And then in the fifth part, we go into the functional unit, so part of the life cycle assessment. And yeah, we will explain how we approach it for the PROGENY project. So let's start. I hope you can all see the screen and my small laser pointer with the 4 different phases of the life cycle assessment. But before we go there, we have to define what is actually a life cycle. So we're not just looking at the product itself, which we use. We also have to take a look into where is it coming from. So how is it manufactured and what is needed to manufacture it. So the resources which are going into that. Then also the distribution, is there a long distribution way? Then we also should think about the end of life of the product. And also if there's maybe a recycling step involved, because all of that contributes to the impact of this product. Life cycle assessment is the quantitative method for the environmental assessment of product systems over the life cycle. And that's what we are going to talk about in this session. But what impact has the product system? Well, we have to see that like each of the life cycle step will have some emissions, and not just the mining part, also the construction part, the assembly, for example, then also the distribution, all the other parts of the life cycle. And all these emissions, they will interact with the environment and with us as well. So they will go in different areas of protection. For example, human health, then also natural resources. What do we need actually? What is mined? And is this in a way affecting us? Do we have to protect that? And then also carbon footprint, very hot topic at the moment with climate change. Then also water footprint, ecosystem quality, and there are many more. This is just an example. Why do we do life cycle assessment? Well, we want to avoid to shift the burden by quantitatively mapping trade-offs to, for example, other life cycle phases. You all know the zero emission car, which is not just zero emission because the mining of the lithium batteries, you'll know that it's still quite dirty and makes the overall product dirty. Then also to other substances like BPA. We can exchange BPA in our plastic bottles, but right now is it changed to another chemical which is equally bad. And we also want to map if the trade-offs are exported to other locations. So is our waste, which we recycle in a really nice way in Western countries, what's happening afterwards? Is it just sold to other countries, and what's happening there? Or to other environmental impacts, like, for example, biofuels, or even the future. So here you can see the 4 phases of life cycle assessment. And we have the goal and scope definition, where we define the research question, the functional unit, then the inventory analysis. I will go into more detail for each phase. And then the impact assessment, and then the final step, the interpretation. And all of these steps are connected in a way, and it is an iterative process, and it needs also some maintenance. We can use it, for example, for product optimization, so the development. We can use it for strategic planning, public policy making, or maybe also product placement. Now you have the same layout on the left, and that's sort of the guideline in which phase we are. This will repeat over the slides. And we start with the first slide, the goal and scope definition. I already said here that we define what a functional unit is. We will go into more detail later in the, I think it was the 3rd session. And also the challenges we have for ex-ante life cycle assessment here. So goal and scope, there we define also the system boundaries, for example. Do we just look at a newspaper, just the production of the newspaper? So it's gate-to-gate life cycle assessment, or do we take a look at also the different resources which are going into the newspaper production, which would be then cradle-to-gate life cycle assessment. Ideally, we look actually at the whole life cycle. So we want to aim for cradle-to-cradle life cycle assessment and really take a look in the whole life cycle to assess it completely. Okay, then we go to the next step. What is required to provide the function of the product system? So here you can see a nice picture of the environment, but we also have the economy where we produce our product. And this economy has like a lot of economic flows which are needed to finally get to the product which we are aiming for. And all these different economic flows, they interact with the environment. And these interactions then can be measured, and then we can say something about the impact to the environment, or what kind of impact it has on the environment. And all these white boxes we call unit processes. And that's in the second step of the life cycle assessment. It's called the inventory analysis. It's also the most time-consuming part usually in life cycle assessment, because here you really have to find what kind of processes lead to our final product, what we are looking at. So in this graph, you see sort of the same as before, just one white box is picked out, which we call in life cycle assessment unit process. And we have the economic flows, so what is going in, like we have different goods which are going in, services, materials, energy, or maybe even like waste treatment. The same can go out. And then we have also the environmental interventions, because all of these processes might, for example, release some CO2 or something else, some chemicals, which are then released to the environment. So that's basically what we do in the inventory analysis phase. And then we get to the next one. What are the consequences? So here we take a look into the impact. And this is called impact assessment. We have different ways, different categories, impact categories we can take a look at. This is also defined in the goal and scope, where we ask our research question, what we want to take a look into. Because different products can have different effects on, for example, land use or the ecotoxicity. And we try to figure out which impacts should be assessed at least. Usually we take a look at all of them. Here again, the environmental interventions are going into these impacts, which can be CO2 or methane or carbon monoxide. All of these three are going, for example, into the impact category climate change, and the characterization factor would be the global warming potential. So they have different kinds of also units. For example, for climate change, it would be CO2 equivalent, which can easily be, I think it's a value which is understood quite easily, but it's not meant like everything is CO2. For example, methane has a bigger impact than CO2 on the climate change. It has a higher global warming potential. Then there are all other impact categories as well: human toxicity, ecotoxicity, acidification, eutrophication, and many more. Then we go to the last step, the interpretation phase. Here I picked an example for hydrogen production. There are different ways how we can produce hydrogen. Most of the time, it's still produced via steam gas reforming, but there are also other ways how we can produce hydrogen, and I hope this will shift also in this direction in the future. On the right side, you can see what we have as an output of the life cycle assessment. For example, we can do a comparative analysis between all these different ways to produce hydrogen, but we can also look into the different unit processes which lead to this product and see which of them are sort of good in a way or bad in a way, which have an impact. Here I chose, for example, climate change. Which I said already is given in the kilogram CO2 equivalent per 1 kilogram hydrogen, which is here the functional unit. And then we can also see what kind of the different unit processes in hotspot analysis, for example, add to a bad impact or maybe even a good impact. For example, biomass can take up CO2. That's why here we have a negative value. So what did we learn? We learn about the 4 different phases of life cycle assessment, that we have to define the goal and scope, that we have take a lot of time in the inventory analysis, get our data together, see what unit processes are contributing to our product, which are needed. Then we also have the impact assessment phase, where we decide on which impacts we want to take a look into, and also calculate the impact, and then the interpretation phase. And as I said, this is an iterative process. There might be several loops, so this can be refined if needed. And that's the first part of our session or sessions. And if there are any questions, I don't see any in the chat, then maybe we already may go to the next part, or do you want to say something?
Thanks, Flora. I think this was a good overview to have a common ground and understanding for those of joining us today and who will watch the video later on the basics of life cycle assessment before we continue and build up in the next sessions in a moment on the practice of ex-ante life cycle assessment, which follows and tries to follow the standards, but where sometimes the standards fall short of supporting the analyst when assessing a system that's still at the earlier stages of innovation. So we'll see that in a moment. Are there any questions from the audience that we could answer? Please feel free to use the chat and write up your questions. Just a note, we will have 2 more sessions or 2 more workshops really from PROGENY. This is just part 1. We will continue. There will be a new workshop in April, in the spring anyway, where we will look further into scenario making and software and how to prospectively assess emerging technologies in the future. And then we will continue with the 3rd workshop with more details on ex-ante life cycle assessment after the summer of 2022. But we have Mohammad with a question. Please, Mohammad, write it up in the chat. Write it down in the chat, sorry. I don't see the question yet, Mohammad. Probably still typing. Yeah, let's give it a couple more seconds. Otherwise, we will continue. Mohammad, don't worry, if before the next segment of questions, there will be time to take your question as well. Anyone else, just use the chat. So Flora, I'll suggest we continue, and if there's questions, we will collect them for later. Let's move to the more interesting, or perhaps a newer part for some of the attendants today on Ex-Ante LCA.
Yes, thanks. Okay, then we will go, just a second, to the challenges for future technology and what actually ex-ante lifecycle is. For that, I would like to show this graph. It's a way how we can classify the technology readiness level. And it shows in which phase of the production or which phase of thinking the project is. So, for example, when you are still in the research and development part, it's lower TRL, so technology readiness level. Then, for example, TRL 5 or 6, that's already, you have a prototype, you have a pilot scale maybe. And then higher TRLs are going into the area of the final product, the market release. And common lifecycle assessment just take a look into what is already there. So the product which we can actually buy, for example. So we call this ex post, but not really, because I mean, it's a common lifecycle assessment. The counterpart to ex post lifecycle assessment is then ex ante lifecycle assessment. And ex ante lifecycle assessment takes into account in which technology readiness level we are in. This comes with a lot of challenges as well, but I think also with a lot of opportunities, we will say in a second. Some maybe also have heard the word prospective lifecycle assessment. There's also anticipatory lifecycle assessment or dynamic lifecycle assessment. But here in this session, or in this workshop, we would like to call it ex-ante lifecycle assessment. So you have seen on the flyer maybe this citation of Collingridge, and he said, "When change is easy, the need for it cannot be foreseen. When the need for change is apparent, change has become expensive, difficult, and time-consuming." So this is also referred to as the Collingridge dilemma, but I don't see it like that. I'm an ex-ante lifecycle analyst or researcher, and I see it more like an opportunity. So for that, I want to show you this graph. It's similar than the technology readiness ladder you have seen before. On the x-axis, you see the different technology readiness levels. Here, the wording is a bit different from the concept to the industrial production. And then on the y-axis, we see different things. For example, knowledge, cost, decrease of freedom, potential environmental impacts, going from low to high. So the degrees of freedom, which give us sort of the space in which we can optimize, for example, something, or we have a bigger impact in a way when we change something in a more sustainable way. We can see this curve in purple, which shows quite nicely that at the beginning we have so many degrees of freedom, so many opportunities to change something. And they will decrease the more defined our product is, because then it's quite hard to change things, and we have more an idea about what we will produce in the end. But then also the cost increase in terms of changes. So it's not the final cost of the product, it's the cost of having a change in the final system. And then also the knowledge increases because we know more about a product. Of course, we like to shift this knowledge curve a little bit more to the left. Next, on the life cycle assessment, we want to predict more the future, but we don't like this word prediction. I will come to that later. Life cycle assessment has the biggest impact when we can apply it at the beginning. So during the development of the technology. And it has less impact, of course, in the end, but still has an impact. So it's better than nothing. But it's better if we apply it at the beginning, like in this project. But how can we say something about the future? Because the future is uncertain. We do not know what the future holds for us. Here, like the citation of a colleague of ours, Paul Behrens, he wrote in his book that scientists try to avoid the word prediction because it implies too much certainty in a high complex word. I can't predict what I will have for dinner next Thursday, but I can make reasonable dinner-based scenarios given the food I like and what I am capable of cooking. In his case, it would be beans on toast, probably. This is a big topic in life cycle assessment. So the development of scenarios. That's why we want to dedicate for that another workshop. And we plan to plan this in spring 2022. Scenario development is sort of in the goal and scope definition and also in the inventory analysis part. Then one part in the inventory analysis, which is quite important for ex-ante life cycle assessment, is, yeah, we have to take a look again. You don't know this graph yet. That's why I quickly explain it. It's similar to the one before. We have again the environmental intervention. So the environment is here on the outside. And then in the inside this time we have two different classification. The orange part are the foreground processes. So we have a control about these processes. So the technology developer have a control about them. They can change something in there. And then we have also the so-called background processes. Both of these parts belong to the economic flows. The background processes we usually use for that databases, for example, EcoInvent, or I don't know, lifecycle practitioner know about this. So there we have some aid in a way that we have access to databases, for example, for the production of some chemicals which are quite common and well known. In ex-ante life cycle assessment, we have this challenge that we have to scale them up. So because we want to take a look not just at the state where the product is, so which kind of technology readiness level, we also want to look into the future, how the final product will look like. So we have to scale up the foreground, but we also have to scale up the background because all these databases are state of the art. So they are sort of more in the present, not in the future. There are ways, there are already some nice work done, for example, for the energy mixes. Yeah, but we have to take this into account in ex-ante life cycle assessment. Let's make an example. So a student of mine is working on a project about microbial protein production, where they use fermentation, gas fermentation, to produce high protein substitutes, for example, for fish feed, to exchange that and not use soy-based high protein substitutes. And for this production process, we need CO2. But yeah, I asked myself some questions, and also the student asked himself some questions. There are already companies which are doing that, and they also, yeah, have to answer these questions. What is actually the market for CO2? We don't know that because it's still quite new in a way to use it as an educt for a process. And do we actually avoid the burden of CO2 by gas fermentation? That was also a big question for myself. So for that, we have to take a look into where the gas is coming from. In the case of this study, it's coming from a biogas plant where they gasify, for example, wood and produce energy. And then they also have the waste stream CO2. In this case, it's a waste stream. But if I want to use it for a fermentation process, it has to be at least a little bit cleaner and it has to be processed. So we have this capturing and purification unit process in between. And then at this part, we say it becomes a product. So CO2 is now a product. But then the question is, how do we calculate the burden when we co-produce CO2 in a process? So there's not just energy going out now, there's also going out CO2. So you see my questions, they open up more questions. Then we try to answer the next one. Do we actually avoid the burden of CO2 by gas fermentations? For that, we have to take another look into the carbon cycle. What you can see here on the right side, as I said, they have this biomass gasification where they produce energy. There are some companies which are doing that, and they use wood, and this wood takes up CO2, which is so far so good. And then we have the fermentation process, and we produce this high protein product, which then is fed to the fish. The fish will also release some of the CO2, not so much, but a bit. Then we consume the fish. We as humans, we breathe, we also produce CO2. And in the end, what we can say is that this is a carbon neutral process. So we do not reduce the CO2, the overall CO2 by this process. It's still good because we produce some food and it has some advantages. We need less land for this production process if you compare it to soy production. There are a lot of advantages as well, but we do not capture CO2. So that's about the ex-ante life cycle assessment. It's just a glimpse. There's obviously more about that. So yeah, what did we learn? We learned about the Colindrich dilemma, and that it's for us not really a dilemma, it's more an opportunity. And you learned about the fact that there will be another workshop and that we have to scale up for and background processes. So that's something that's yeah, different to life cycle assessment in general. Good. And now we try to answer all your questions. I see some have popped up.
Yeah, we can start with a question from Scheidt. I hope I pronounce the name correctly. Does the ex-ante LCA methodology aid in addressing issues of system expansion in the case of a consequential LCA? And how do you see the involvement of different domain personnel that may be required in case of system expansion within the ex-ante LCA arena?
That was quite a lot.
Yeah, so I think I'll give you the floor in a moment, Flora. I wanted to touch on the second part of the question first, and then I don't know how much time we will have to go into the details of system expansion and consequential LCA, but maybe Flora has some thoughts on that. I think in the whole exercise it's crucial to have different domain experts, because as a life cycle analyst or life cycle scientist, if you are also developing methodologies, I think we don't have the full expertise on understanding the detailed processes or understanding how a system might evolve in the future. So you really have to have this tight connection to the technology developers and to the experts to understand how a system may change into the future. So the domain expertise is crucial, and that's why the context of PROGENY or the context of these collaborative projects helps us in understanding how the standard methods need to be updated as well, both in software but also in terms of concepts when you're assessing a system that has to evolve in the future. Also, for instance, where you're making scenarios, you need that level of expertise, and that probably applies also to the context of system expansion. Flora, and then I will take a look at the other questions and then summarize them for you.
Yeah, so system expansion goes in the LA or in the direction of how we allocate, for example, waste streams, or which become then product streams. So I think in this project we tried different ways. In the end, we ended up to use economic allocation. We do also take into account the process of the gasification, of course. It's quite tricky because there are different interests involved. For example, if you're a producer of this microbial protein, you just take a look into the fermentation and what's so on, and you want to sell it, and you have a lot of companies which are involved in this part. For example, the gasification step, the energy production is probably another company. And this company, of course, they want to carbon capture. They want to have this carbon capture label. And so that can be beneficial. So what we are taking a look into is like the different combinations. If the company who is producing the energy and also supplies some of the CO2, it's a tiny amount compared to what they produce on CO2. We have to see that. So we decided against physical allocation in that direction, because we need also a lot of energy for the fermentation process. So we have like different combinations. So what kind of wood then? Also, is there like carbon capture involved by the company who is producing the energy, and also storage? That's something that's also very beneficial, because then you really reduce the CO2, the overall CO2. So there are different sub questions we ask ourselves. So it's not just the one. Is it better than the soy production, or I don't know, fish meal production or something like that? So we also try out a different combination, and yeah, it's quite hard also to project all of them into the future, because all these different technologies which are going this direction. Also, where's the hydrogen coming from? We also need hydrogen for that. They are at different levels of technology readiness. So we have to take this also into account. So it's a big combination of all these things, always taking into the account if they are available in the next 5 years. Are they available in the next 10 years? And when will be like the optimal approach be available? So there's even like that what we take into account. And yes, system expansion in this case, we also take into account this production process of energy and yeah, the CO2.
Right. Thanks, Flora. I'll take quickly 2 questions, and then we will move to the upscaling related ones. So there's a question about why this is an opportunity, and I would say quickly, Martina, there is an opportunity in conducting LCA studies. It's such when a technology is still being designed. In the context of PROGENY, we are talking about a technology that's TRL1. The devices will hopefully are being developed in the context of the project. And those devices do not exist yet. At the same time, as Indra also mentioned at the beginning, the close contact with technology developers and our ability to conduct the assessment as the technology is being developed allows us to suggest or to point the design towards a direction that's preferable, or to at least trying to highlight pathways towards a more sustainable technology or a more environmentally preferable technology. So that's why the opportunity. In terms of definitions, as Flora has mentioned, there's been a lot of contributions into this field of the application of a life cycle assessment to assess systems that are novel, or to assess emerging technologies. We define as ex-ante life cycle assessment the application of LCA when there is an emerging technology being studied, currently at the lab scale or at the lower stages of a TRL scale, and that includes when the assessment is including also a prospective study of how this emerging technology might look in the future, when it will or if it will operate at scale. Prospective life cycle assessment may include the assessment of an emerging technology, but sometimes may be simply a forward-looking exercise when you're assessing. You might be assessing a already well-established and entrenched or commercially available system. So I would suggest I will refer all of you interested in definitions to recent publications in the literature, which have been dealing also with the specific aspects of each nuance on life cycle assessment. We have a question related to, very interesting question related to upscaling specifically. One, Flora, relates to chemical production. For instance, there is a question related to how to take the chemical production route change into consideration while doing upscaling. Some new materials created in the lab have really long and complex synthesis steps. And before such a material reaches the market, the chemical production route might be simplified by chemical engineers because of economic reasons. Simplifying and shortening the chemical production route normally requires another research study, which means right now we only know that the production route will change, but we have no clue how it will change, how to consider this in Ex-Ante LCA. I think this is a question that you have been thinking a lot about in the context of this project as well, Flora, and as also as a biochemical engineer, something that's close to your expertise. And related to that, there is a question whether there are techniques or methods to upscale systems.
Yes, there are techniques to upscale, but it really depends. So as a life cycle practitioner, you usually don't have the knowledge about it. So you have to work closely together with the technology developers. That's the first step. Then, I mean, there's a publication of Pacino. He tried to simplify it in a way how to calculate the energy demand which is needed and so on. They're quite crude estimation, but it's also what the industry is doing when they want to scale up their processes which they developed in their research and development departments. They also have to think about that and yeah, extrapolate it into the future. There are different ways to approach that, and I mean, you maybe know the Pavatka pyramid, which sort of tries to classify the different stages, or not the different approaches you can take in scale up, but they also correlate with how much knowledge you have about the process. So of course, less knowledge means also less certainty. That's why we always recommend to do uncertainty analysis. There is not like one concrete pathway. The best is you gather as much as possible information, and then try to refine it as much as possible. So can you say something about, can you calculate it as like spatial temporally, or is it just possible to use the overall chemical equation to have like a maximum approach? So this is like the maximum we want to reach. There will be some decrease in the yield probably during the whole process, but yeah, that's something you can take into account. And for, as I said, ex-ante life cycle assessment, you as the ex-ante life cycle analyst, you have to think about it, and you have to build your scenarios in that direction. So scenarios development is very, very important. That's why we dedicate another session for that.
Thanks, Laura. There's a question related to how you compare systems. One technology that's still at the lower TRL scale may use newly developed materials, which also might have a low TRL, while other technologies may, your technology that you're comparing, your incumbent system, you're comparing your emerging system to, might use well-developed commercial materials. How do you make sure you're making a fair comparison between those two systems?
Yeah. Working close together with your colleagues, sort of, which are developing the technology, which are experts. So you always have to have this feedback round with experts, not just sit in your tiny room and think about it and plan these big scenarios. You always have to have this feedback and yeah, have to ask experts if this makes really sense.
Yeah, and also I think you should be specific in establishing a fair comparison during your goal and scope phase of your life cycle assessment study, if it's a comparative study. And you should look also in the type of data you're using, in the temporal boundaries of your system, together with its geographical boundaries, for instance, which specific data step do your background data have? And same thing for your foreground data. How do you make sure that you're comparing systems that are taking similar assumptions on the data as well? So those are all the important questions that are also come into the picture when you are creating future scenarios and where you are comparing systems that and you want to make a fair comparison. Therefore, you would have to establish this comparison and detail this comparison also when it comes to the time specification of the data. There is a question related to uncertainty analysis in ex-ante LCA studies. I think in general, to do an proper uncertainty analysis, you need data, and sometimes you have scarce data availability when you are conducting an ex-ante life cycle assessment study, which means that you may park a formal and quantitative uncertainty analysis and opt instead for an assessment of which potential data sources or assumption in your system may be driving a lot of your results. And then at the later stages, when you're assessing the future system, for instance, you may be opting for a quantitative uncertainty analysis. It's not always the case, especially in the context of ex-ante life cycle assessment, that a formal quantitative uncertainty analysis will allow you to get greater information on your system. You already know that there's a lot of data that are uncertain. You already know that your results will be already representative within the context of the study that you're establishing, with the context of assumptions and the system of assumptions that you're using, which means that you may not need a quantitative uncertainty analysis, but you need to have the conversation with technology developers and with all the practitioners involved in the study to understand which potential sources and data points are driving your uncertainty. And in a comparative setup, there's been a lot of work in standard LCA, but also that applies also to ex-ante LCA, which allows you to model the system, model a quantitative uncertainty analysis in a way that allows you to understand how one system compares to the other. I would also add that it's important also to do a sensitivity analysis, which would allow to understand which decisions you have made, both in the foreground, but also sometimes in the background, that contribute the most to the uncertainty of your results. Yeah, we have a comment related to how much the expert don't know, and sometimes it's true. We have also learned there's also some specific pathways or some knowledge that it's still not in the hand of the technology developer, even though they're expert in a specific technological domain. In that case, it may help to look at the historical evolution of technology, unless your technology, like in the context of PROGENY, is disruptive, is a brand new technological setup. Sometimes, but even in this case, and I think Flora will show you some of these aspects in the latest session of this workshop. Even in such early stages and with disruptive technologies, you may be able to learn from historical evidence of how similar systems or technologies operating in the same cluster may have evolved in the past. There might be some commonalities, some processes that are not used in the lab now, but we know that they might be used when a technology might perform at scale. So it's, while you don't have the full knowledge by studying systems and how they've evolved and studying innovation, how innovation evolves, you may be able to understand how a system may look into the future. All right, Flora, I think we can continue to the next section. Thanks a lot for the very good questions, and we will have time for more questions after the next bit on the functional unit.
I see already more questions are popping up, but we saved some time later. I hope that's fine. So let's go to the next part. So here we dive in again a bit more into conventional life cycle assessment, and a quite big topic, especially now in the case of the PROGENY project, is how we define the functional unit, and I will show you why. So what you can see here, that's like similar to the drawing about the life cycle. It's now laid out. So imagine there's another arrow going back again. So why is the functional unit so important? Because everything that's calculated in life cycle assessment so the impact on the environment is calculated in the relation to the functional unit. So it can be that we just use a itsy tiny bit like amount of transportation because it's not really necessary. But transportation in general can be quite, bad for the environment. But in terms of the functional unit, so like a product, it could be, I will show you later what it can be, the functional unit. Then do we need like some chemicals, maybe also a very tiny amount, or how much do we have to mine something for producing these chemicals, for example? And all these unit processes, sorry, wrong direction, they will have an emission. And as I told you before, these emissions or other interactions with the environment can also be land use, for example. They will be then the impact which we can quantify. So everything is scaled to the functional unit. So how do we define the functional unit? How do we figure out what is the functional unit of our process? So if you want to make, let's say, good life cycle assessment, you should at least go to the use phase, which is quite tricky sometimes for Ex-Ante life cycle assessment. So the use phase would be the use of, for example, a light bulb to light a room. And not just producing one light bulb. So it should be also like, for example, the energy which I need for producing light. So the use phase. So we have 4 different things we have to define. So what is the function? Then what is the functional unit? And are there any alternatives? And which of these different functional units we declare as the reference flow? I like to explain that with some examples. So we have the coffee to go example. Have you ever wondered when standing in front of a coffee shop, how is this mug actually produced? How is this cup produced, which I'm using right now to drink out? Is there a way to optimize it, maybe to make it more sustainable? So the question would be, which of the processes involved in the life cycle of a disposable cup can be optimized in terms of environmental impact? You might already know where this is leading, so it's more hotspot analysis. The function would be, in that case, to keep, for example, 250 milliliters of a hot beverage, in my case it would be coffee, ready for consumption. So that's the function. The functional unit is a bit more defined. So, for example, the use of one average disposable cup to keep 250 milliliters of a hot beverage ready for consumption. In this case, because my research question, which I'm asking, I just want to take a look at the specific cup. So there are no alternatives, and I don't need a reference flow because I just have this functional unit. But no, before I get there, so for the functional unit, it's very important to be quite precise. For example, ask where will it be produced? Then what kind of material will you take a look into? Is it more a plastic cup, or is it a paper cup, or what is the lid made of? Do you include the lid? Then also, where will it be disposed? Is it more here in the Netherlands, or is it in another country where they have less good recycling systems? So it makes a difference. So try to be as precise as possible in the functional unit. And as I said, the functional unit definition is part of goal and scope. This also goes a little bit in the scope of life cycle assessment. Okay, so next example. Now I actually want to change some of my habits. Each morning, like 5 times a week, I go to this coffee shop before work and get my cup of coffee, and then I go to work. But I'm thinking, okay, I want to change that. I want to change it to maybe using a reusable cup. So I'm going to buy a reusable cup and I want to see if this is really more sustainable. So the function will be the same. It's still to keep 250 milliliter of a hot beverage ready for consumption. But now I have to think about a functional unit. So what would be the functional unit? What makes sense? Is it just comparing one cup with another? Or as I said, we look more in the use phase of the product. So maybe just take a look into 1 year. This can be also months or I don't know, but I think I wanna take a look into 1 year. Because I think the new mug, the new cup I'm buying, it will at least hold that long, maybe even longer. That would be nice. But yeah, then as I said, I do this 5 times a week. So we have also that now in the functional unit. And now we have alternatives. We have the disposable cup and we have the reusable cup. And we have different, different alternatives. And I decide the reference flow will be the disposable cup. But it can also be the other way around. Let's have another example. As I already explained at the beginning, or some minutes ago, I want to now change a light bulb in my sleeping room. But I'm a bit confused. I don't know which one to choose, what is the best one. And I'm quite sensitive to environment. I want to make a right choice, that it's the most sustainable version. But yeah, the LED, they say it's so good, but it's so expensive. I really want to be sure if I'm buying a more expensive LED. So what would be the function now if I'm conducting a life cycle assessment? The function is to illuminate a room. So to shed some light in my room. The functional unit would be illuminating a room. In my case, it's 40 square meters. And for 1,000 hours, it usually says that on the prescription or on the package of the light bulb, or I think even more hours they last. And then I want to have it quite like illuminated. I want to have a high lumen amount. And yeah, now I want to take a look into the different alternatives which I can buy. So the tube, maybe a fluorescent one, maybe incandescent or LED. So now I have these different alternatives and I decided again, the reference flow will be the LED because that's the one I'm most interested in. Can also be another one, but everything is then in comparison to this. Oh, the takeaway here is now I have so many options. Maybe it's too much to calculate and not all of them make sense. For example, I can't use a tube. I don't have the connection for that. I can just screw my light bulbs in. So I can already define my functional unit a little bit differently to exclude this one because it doesn't make sense in my case. So what I want to say with that is the more strictly you are, the less alternatives you will get. The more strictly you are with defining the functional unit. And that's also the takeaway of this session, that we have to be very precise, and the functional unit is very important because everything will be calculated around this functional unit, so the whole impact. And we have to choose it wisely to really compare different products if we want to compare them. And yeah, the fewer alternatives we get, the more we describe it, of course.
Yeah, thanks, Flora. This is an important part of this story because even for trivial or admittedly trivial or not system like cups, you need to make a lot of decisions in standard practice, and that system of decisions may be even more complicated when you are dealing with emerging technologies. And we will see the example of PROGENY in a moment. What can you do as an analyst when you are in the early stages of innovation and when someone is still being developed, a technology is still being developed? Of course, as an analyst, you will have to immerse yourself in the specific technology system. You will have to speak quote unquote the same language of the technology developer and get to a deep level of understanding how technology operates. That specific, the definition of a functional unit will also be important, and that relates to one of the questions I see in the chat. To which system would you compare your emerging system, and how to make a fair comparison, which we were talking about before. First of all, you will have to identify the incumbent system. You will see that that's not always an easy activity for the analyst, and in the fourth and last session of this workshop. And also, you have to, as I was mentioning before, you have to take into account that there is an element of evolution and innovation also for the incumbent system that you might have identified. Also in the context of light bulb, standard and commercialized light bulbs might improve or change or be adapted or evolve as time goes by. So if you're doing an assessment that's looking into 20 years from now for your emerging technology, imagine you have a new generation of light bulbs that you are working on. It's just an innovative light bulb that never existed before, that uses principles that are new to the market, and you're comparing with the standard light bulb. If you're making this comparison now, you will make certain assumptions on how to compare the systems, on the data, on the temporal and geographical boundaries. If you want to project this comparison into the future, you will also take into account that the incumbent light bulb on the market will also be changing. And all of this consideration you will need to make. And I will recommend you to take a look at the recent development in the methodology. From our group also, there's been a lot of very interesting publications from a lot of research groups around Europe and in the globe on this topic. And maybe I'll post a couple of those examples in the chat in a moment. Are there other questions related to this last presentation related to functional units? I think again, what Flora is just presenting was for those of you who are LCA savvy, a repetition or a refreshment of known concepts. But let's try to and keep in mind the basics when you're switching. And you will see in the next session in a moment, we are switching from standard practice and systems are known and available at scale and well entrenched into our economy, and shift those kind of questions that Flora was asking herself related to her coffee purchases and habits to a system that's completely new, which we'll see in this next session now. I suggest, Flora, you go ahead with the fourth and last session.
Yeah, thanks for the nice transition. Okay, then let's repeat again what the PROGENY project is about. Well, PROGENY stands for Proto-Opto-Electromechanical Hybrid Systems for Generation Next Bionic Devices. So I think that's now totally clear for everyone. It's quite complex, but there's a reason behind that. If you want to read more about the project and who is involved, I think Stefano posted already the link to the webpage. There's more information than that. I'm showing now the challenges from the ex-ante life cycle perspective with the focus on the functional unit. That's why we had this session before. Yeah, basically PROGENY is about soap bubbles. But that's not all there is to it. So it's about designer soap. So designer surfactants in more detail. So let's dissect a little bit this long explanation of PROGENY, the abbreviation. So we have this proto, which means that this designer soap, we can call it, has some protonic properties. So it can, for example, potentially interact with the nervous system. So it can be used for maybe bionic devices like prosthetics. So that's a bit the hope, and we want to aim for that as well. But we are quite in early stages, but it's a possibility, and it's one of the properties of this designer soap. Another property would be that it has optical properties. So you can, and there's a nice example on the right side, already project something on this. So maybe there will be in the future screens made of soap, of this designer soap. Then it has also electronic properties. So we also aim for revolutionizing in a way the semiconductor production, for example. So very quite, as Stefano already said, a technology which can, sort of change the way we think about incumbent technology at the moment. So it's quite disruptive in a way. And it also has mechanical properties. So it can, if you use sound, for example, it behaves like a wave in a way because it's like a membrane. So there's like a lot to it, a lot of potential, and also so many functional units you can define. It's very tricky. So what do we do with that? First of all, we are quite in an early phase of the project. We have now almost 1 year. The surfactants are produced. They will be ready, I think, maybe even today, I don't know. So it's the first round of the surfactants. We have one-dimensional ones and two-dimensional ones, which then make up this designer soap or scientific soap, if you want to phrase it like that. Then also we have the production of some chambers which can hold this soap, where we can do some testing and really check out the different properties and how it behaves. But we are still in a very early phase of this project. It's set for 3 years. Okay, again, back to this slide with the technology readiness level. The PROGENY project is partially in TRL1, but also in TRL2 or TRL3. It depends on which part you take a look into. So as I said, the chemicals or the surfactants, they are still in the making. So that's also quite tricky for us. The chambers are sort of ready, I think, now, but yet it's an ongoing process. So what do we do with the functional unit? Well, since we have so many potential applications in the future, we can write a sci-fi book about it probably. And at a certain point, we will start to think about and dream maybe a bit about what we can do with it. It will get more concrete, but it's where we are at the moment, but in terms of functional unit. So from the life cycle assessment part, the Ex-Ante life cycle assessment part, what we did, or I think is the only thing what you can do at this moment in terms of the functional unit, is we take a look, okay, how or what do we know actually about it? So we know that any kind of device which we will produce in the future will contain of our surfactants, so of the soap film. We will use some metals, plastics, whatever to hold it. We don't know about them yet, really. So the chamber, we just put it aside for now. But we know that we will need the surfactants. Then we also know that probably for the assembling, we need, for example, a clean room to do that, so that it will not be contaminated, or we have some particles in there. So we will also need probably, maybe, we don't know, the clean room. So these two inputs in the assembly, for example, the unit process assembly. Now we see we already switched from the goal and scope, where the functional unit is defined, a bit more into the inventory analysis, but we will go back to the functional unit in a second, because what we do know, we know what we need. We don't know how much we need, for example, for the film, the soap. And we also don't know how much we need the clean room. I will go a little bit into that in a second. But we can now divide our assembly unit process in some sub processes where we can define a functional unit. So what we can do is we start to define new functional units and take a look into the different aspects how this will be produced in the future, because we know these parts will probably be used. So let's have a look into the clean room use. It's an interesting topic because there's not a lot of data available. It's either quite outdated, or all the industry we try to reach out, they have different opinions, they have different energy densities. So there's not like a common practice about it in terms of life cycle assessment, how we include it. So we know from other projects, which are also ex-ante life cycle assessment projects, that, for example, for the PV production, photovoltaic, that this will pop up because it needs a lot of energy to maintain a clean space. So basically a clean room is just a clean space where we can assemble, for example, technology. So what is the function? As I said, the function is space, which assures a certain cleanness. So how many particles are allowed, what size of particles are allowed. So there's some ISO standards behind that. And the function would be very generic in this case for now. The use of a certain amount of square meters of this clean room for a certain amount of time to build, for example, one technical device with a certain quality. So we might also allow some of impurity. And then alternatives can be now in this very generic way. For example, I want to keep it generic because we want to broaden this a little bit and take a look into different kinds of ISO standards. So the different level of cleanness, for example, ISO standard 1 is very, very clean, which is applied, for example, to produce aerospace technology. And ISO standard 9 would be well aerated office space, for example. Semiconductors, for example, are produced more in ISO standard 5, where there are a certain amount of particles allowed, and so on. So let's zoom a little bit out. We have now a functional unit. In the inventory analysis, we figured out which kind of unit processes we need. So what's important, so input values like the energy density of a clean room, then also the throughput, because that's sort of the scaling factor, how much do we need it. Then equipment, which is mainly the production area. The materials, they usually don't factor so much into that, but usually we always try to also calculate it as well, just in case this can pop up. And then, of course, the classification. So what kind of cleanness do we want to reach? And this can be even zoomed out more. This goes now a little bit more in the next workshop about scenario development, which is part of the goal and scope and inventory analysis, sort of. It's going in this direction the most, but also a little bit into interpretation and uncertainty as well. But you have seen the graph has usually arrows going in all the directions for the different phases, so they are quite interconnected. So it's very hard to distinguish, okay, it's just goal and scope, it's just inventory analysis. So we can zoom out more and think about if we want to take, for example, a look into different climate zones. Does this change anything if we have like more arid climate or so on? So that's also what we try in this part, to see if there's a better way to produce technology in the future when we take into account the usage of clean rooms So is it better to produce a semiconductor in a clean room, which is in Germany, or is it better to do it in Taiwan? I mean, of course, we also have political things which are popping up. So this is all going into scenario development, where you can take into account this kind of parameters which are not directly involved in life cycle assessment. Yeah, okay. I think that's about the challenges of the functional unit in the PROGENY project and how we approach it as at this stage where we are.
Right. Thanks a lot, Flora. I think this was an important part to show the challenges, and you see now in a system that's still at an early stage of development, there may be many rabbit holes, and you have, especially at the beginning of the process of analysis with life cycle assessment, pick your battles and select on the basis of the goal of the study, as it's put in the chat as well. Depending on the goal of the study, selecting the specific functional units that are relevant. Before we go in more Q&A and take more questions from the chat, maybe I would like to hear from Indro. You know much more. You are the expert together with our project partners on this specific technology, and maybe you wanted to add something on the technological setup and some aspects, some details of the technologies before we move on other more LCA related questions.
Yeah, just a few pointers. The first is that maybe many of our audience may not know what surfactants are. Surfactants are just a way of, it's a classification of molecules which are just the soap molecules that we have. So chemists have designed soap molecules. It's a class of molecules. It's like hair on your skin that sticks out. Part of it sticks out from the water surface, and part of it actually is inside the skin. So it's part of it is hydrophilic and part of it is hydrophobic. So there's a tail that sticks out of water surface in surfactants, and there's a head that dips into the water surface into surfactants. So it's a very specific class of so-called bipolar molecules, part of which is water-loving and part of which is water-hating. Now, chemists have developed so far synthesized surfactants based on their functional, as a functional unit to wash clothes mainly, to be used as detergents, and also for stabilizing some colloids. But no one is stopping us with our current technological understanding to make soap molecules which can be, for example, catalysts for reaction, or they can be semiconducting molecules. So in our project PROGENY, we are using semiconducting molecules and functionalizing them to make soap. So this is the basis that we need to know about the PROGENY project, and that's all I wanted to say. Thank you.
Yeah, thanks, Indro. I think those were important important points to clarify. And you're right that the audience is varied, so some might have missed otherwise some of the details. But thanks a lot. We have a question related to functional units. There's Nashmin saying, depending on the selection of a functional unit when you're assessing two technologies, for instance, when you consider a functional unit based on input material, a specific technology was more efficient because it could produce higher amounts of products. While considering functional units based on output of product, the technology 2 was a better option. So Nashmin is wondering which functional unit is more reliable and accurate. What would you say, Flora?
Yeah, so I think it also a little bit depends. So we have this challenge in another project a bit where we focus on bio-based products. There it makes also sometimes sense to focus on the input. So what do we use to produce a certain kind of chemical? So is it more from straw residues or also so on? Yeah, it's difficult to say. It really depends what aspects you want to take a look into, and it makes sense to. So what I experience is it sort of changes sometimes the functional unit, while you discover and figure out what all the unit processes are leading to that. And I think that can happen in ex-ante lifecycle assessment. And at the beginning, you follow all the guidelines and you start with the functional unit, but then you figure out, okay, there are some hotspots from my first analysis. Maybe it's better to change the objective in a way. So I'm not sure if there's like a best practice to that. It's really tricky. It depends what should be the outcome of it. So what is the question you're interested in, and also the other parts which are involved in the life cycle assessment. What do they want to have as the end product, sort of? What do they want to compare, for example?
Yeah, exactly. And the goal of the study, the Sean Zhang is referring to, is a very important thing to always keep in mind. We also say that in the practice, in our experience with a number of projects across multiple, a variety of technology and at various stages of a TRL scale that the Flora has shown earlier, our experience that you may need to consider a variety of functional units as you go, because these systems are evolving. And have a discussion, entertain that discussion with the technology developers and the decision makers on under which circumstances a technology, if it's a comparative study, is performing better than an incumbent. If it's a hotspots kind of assessment, which aspects of the technology or the design should be designed out during the development of a technology because of potential future impacts, potential future technological lock-ins. So those are considerations, and this iterative nature of the study is an important one to keep in mind. Do we have other questions related to any of the aspects we have been talking about this morning? I don't see any new question. Of course, feel free to reach out to us afterwards if you still have pending questions, and interact, as Indros mentioned at the beginning, on the PROGENY forum on the website. Again, the recording will be posted on our channels, on our YouTube channel for the PROGENY project. And a last note: stay focused on our website and take a look regularly. As announced by Flora, we will have, mentioned by me before, we will also have a follow-up workshop specific on scenario methodologies, also with a look into open source software applications that are coming out of the PROGENY project and other projects that we, as Leiden University and with our partners have been working on.
Yeah, now you also know what the next workshop will be about. If you know about some groups which might be interested in scenario development and also in the next workshop, let us know, and yeah, repost. We try to use again LinkedIn and the webpage, but we yeah, are also open to you can sort of forward the link and share with other colleagues which are interested in this topic.
Yeah, and we will keep on using the PROGENY project to showcase our results and the new methodologies that we will develop in the context of this project. So that's the idea also for the next workshop. All right, I don't see any question in the chat, so I would like to thank Flora for taking us by the hand through this world of Ex-Ante LCA, or at least giving a starter and some food for thought for the practitioners. Indro for his technical expertise and for initiating this workshop with UASABI Innovations, the European Commission for supporting our PROGENY project, and all of you for attending this workshop. Thanks a lot.
Thanks.